Okay, thank you. Thank you, everyone. Thanks for coming to this talk. Our talk is about Apache Spark Apache HBase connector, and it's a library to support Spark accessing HBase tables as external data source. With it, user can operate HBase by Spark SQL. So first, a little about ourselves. I'm Wei-Qing Yang. I'm a software engineer at Hortonworks. Contribute to Spark, HBase, and Barry, and Hadoop. So.
Yeah, this is Minjue. I'm come from Hortonworks as well. I work on the Spark and the Spark-related ecosystem, Spark SQL, machine learning library, and Spark streaming and other things.
Yeah, okay, this is our agenda. Today, we will talk about the motivations of this connector and give an overview about it, why it's good for use, and what's its architecture and implementation, and how to use it. And then we will do a demo. So why we need to develop a new Spark HBase connector? Before starting to develop a new connector, we try to find if there were existing connectors we could use directly. There were several open source Spark HBase connectors available, neither as Spark packages or as an independent project or in Apache HBase trunk. So we needed to evaluate our solutions. First, we needed to decide at which level this connector should be, in RDD level or data frame level. The HBase connector in HBase trunk has a very rich support at RDD level, but its data frame level supports was not rich at that time. So also its design, which relies on the standard Hadoop RDD with HBase built-in table input format. That design has some performance limitation. On the other hand, the Spark has moved to data frame and dataset APIs. So the end user prefer to use data frame and dataset APIs. So we decided to make the connector at data frame level. And there were also some, okay, sorry. So there were also some other connectors in data frame level, but their design are very complicated. For example, they apply very advanced customized optimization by embedding its own query optimization plan inside the standard Spark Catalyst engine, ship the RDD to HBase, and performs the complicated task inside the HBase coprocessor. Those approach are able to achieve high performance. But as we know, Spark evolves very quickly. It's very difficult for them to maintain due to its complexity. Then we have to develop a new connector to overcome those potential bottleneck and weakness. In the following talk, we will call this Spark HBase connector SHC briefly. SHC leverages Spark Catalyst engine for query optimization. Use HBase as fast access key value store, implements the standard Spark data source API. This design makes the maintenance very easy, while achieving a good trade-off between performance and simplicity. Since no matter how Spark changes, the data source API keeps stable. And full-fledged data frame support. The HBase data frame is a standard Spark data frame, so user can query data by Spark SQL. And if the user is familiar with data frame APIs, they can use integrated language, such as join, select, and so on. Although we didn't do any optimization with HBase coprocessor, but we do care about the performance. We didn't use standard HBase RDD. Instead, we construct the RDD from scratch in order to achieve high performance. With this optimized RDD, okay, I think, sorry. So so with this customized RDD, all the credential techniques such as partition pooling and data locality and column pooling, predicate pushdown, all this, we get good performance based from these two features. How to achieve all of this, we will talk about it later. Use Spark unhandled filters APIs is an efficient optimization. This API tells Spark about filters which has been implemented in S3C as opposite to return all the filters. Without implementing this API, Spark will reply all the filters once the data returned from the HBase. That can that can sometimes reapplying all the filters doesn't change doesn't change the result, but sometimes sorry, it's in this stage. But sometimes, if the filters are very complicated, it will be very expensive. So catch Spark HBase connections. S3C did catch any connections objects at the very beginning. Spark and the cost to create connection was done each time when S3C needed to visit HBase tables and HBase regions. In Apache HBase master, it doesn't have connection pooling under the hood, which has been removed from HBase master code. The connection creation is a very heavyweight operation, and connection implements are thread safe. So for long-lived processes, it will be very useful for S3C to keep connections cached. With this feature, S3C decreased the number of connection creation and greatly improved the performance. To save data in HBase, we need to convert the data type to HBase byte array. This connector has different data coders. Users can choose one of them based on their needs. First, primitive type. Primitive type coder is a custom serialization, use a simple native encoding mechanism. It's use HBase encoding and decoding and do extra works to resolve the order inconsistency between Java primitive type and byte array. S3C can use it to support Java primitive types like int and string. S3C also supports the Avro format natively because it's a very common practice to persist structured data into HBase as a byte array. User can persist Avro records into HBase directly. S3C fully supports all the Avro schemas. Internally, the Avro schema is converted to a native Spark Catalyst engine, Catalyst data type automatically. And users can refer to the example and test cases in S3 GitHub repo for exact usage. For the Felix type, for the Felix type, user can configure if they want to use Felix encoding and decoding instead of primitive type and Avro encoding decoding. Given the popularity of Felix data as input to HBase, its nature to support HBase encoder and decoder in adding to Avro data. Although defaulting to the primitive type coder seems to be susceptible to future changes. For example, with HBase going forward, the backwards compatibility needs to be properly handled. And Felix encoder and decoder support composite key very well. So the default HBase needs to use a more standard and well-tested format like Felix encoder and decoder. Users can also implement their own data coder because HBase supports plugin data coder. HBase can run on the top of the existing HBase tables as long as they follow Java primitive type, ever record, or the data format the plugin data coder supports, and of course, Felix data types. Support composite key. For example, in this cat definition, users choose Felix as the data coder, and the row key has 2 dimensions. One is key 1 and key 2. One thing we need to pay attention to is we only do optimization for the first dimension of the composite key. It's very challenging to do the optimization on other dimensions of the composite key. It will be our future work. So let's look at the architecture and the implementation. As the diagram shows, we assume Spark and HBase are deployed in the same cluster. Spark runs along with the HBase. This part is in Spark side, and this part is in HBase side. Spark's executor are collocated with HBase region server. This deployment can get benefit of data locality, but of course you can choose to deploy Spark and HBase in different clusters. But in that deployment, it won't get the best performance. So when a query comes in like this, the driver compiles the query. And then we can know the filters and required columns from Spark Catalyst engine. Based on the region server's metadata, like the region start point and end point, we can construct the RDD partitions. In Spark, as we know, one partition corresponds to one task. And HBase makes one partition corresponds to one region server. The driver aggregates scans and gets based on the region's metadata and generates one task per region server. If a region server doesn't hold the required data, that region server is not assigned any task. Actually, this is a partition pruning. Note that the driver is not involved in the real job execution except for scheduling the tasks. This avoids the driver being the bottleneck. The tasks are sent to the preferred executor, and the executor will perform the tasks on the local region server. It means the tasks are performed in parallel in the executors to achieve better data locality and concurrency. At high level, the connector treats both scan and gets in the similar way. And both actions are performed in the executor. A task may consist of multiple scans and buckle gets, and the required data in the task is retrieved from only one region server. And this region server will only be the local preference for the tasks. And let's go to the implementation. First, the partition pruning. Tasks only perform in the region server holding request data. There may be a lot of region server in the HBase cluster, but we only send tasks to those region servers who has the required data. All other region servers, if they don't have the data, we don't do anything on them. From the query, we can split the filters into multiple ranges. In HBase side, each region has start point and end point. Then we can do intersection with the regions and the region servers start point and end point. And then we can know if there are required data for this specific region server, which scan range fall into this region server. If we do this for all the region servers, then we can know which region server has the data and which region server doesn't have the data. Also, for the region server holding the required data, which scan ranges are in that region server. Based on this information, we construct RDT tasks and then send them to the region servers holding the required data. In the same region server, there may be multiple scan ranges. So this is how we implement the partition pooling. So the next, data locality. Data locality means we need to move computation to data. In S3C, it means we need to move RDT tasks to the region server. How to gain data locality? We have known which region server has the required data and which scan range are in that region server. Also, we can get the host of the region server from the HBase metadata. Then the left thing is very straightforward. For each task, we just need to set the preference location to be the host of the region server. Column pooling and predicate push down. So column pooling, and for column pooling, we get the required columns and filters from the Spark Catalyst optimization engine. We construct all the required columns to be scanned and barcodes. Maybe there are thousands of columns in the HBase table, but a connector only retrieves required columns from the region server to reduce the network overhead and avoid redundant processing in Spark Catalyst engine. For predicate pushdown, existing standard HBase filters are used to perform predicate pushdown without using any HBase coprocessor. Inside the region server, records don't match the required condition. They will be filtered out. We put those filters like larger and equal string start with to the scans and barcodes and ship them to the region server. The region server will do the filtering for us. Scan and barcode get. We group scan and barcode gets by region server. So we send multiple scans and multiple barcode gets to the region server. Internally, the while clauses are converted to scan and get. And the iterator of row is returned to Catalyst engine for up-level processing. You may be wondering why we group the scans and gets by region server. If we don't do that, and just make each get and scan per task, then as the picture shows, the task number will be more than the number of the region servers. Then we need to send some task to other executors or wait for finishing the first wave of the task and then do the second wave of task. So the next part is how to use SHC, and then we'll do a demo. So how to use SHC. So this is SHC GitHub repo. For the detailed information, please refer the README files here, which is kept up to date. S3C is a open source project. So feel free to download it and use it. You can submit your issues here, and also you can propose the PRs here. There are some examples in the example folder. You can refer them to understand how to use S3C and write your own application. The README file also introduced the detailed usages here. In this part, this is introduction for how to run S3C in security cluster. Spark only support use cases which access a single secure HBase cluster due to its static token acquisition. It doesn't support the ability to dynamically talk to a new secure service after the application has launched without a new start. For example, talk to a new HBase cluster in a streaming application. If your application want to talk to multiple secure HBase cluster, you can use S3C Credential Manager. Now you can refer the doc here for the detailed information. So we have already committed some of our code change to Apache HBase Jira. If you are interested, you can go there. So next, Minjie will do a demo for this.
Okay, thanks for watching the great talks. I think everybody remembers that the overview about Spark HBase connectors. What I want to introduce here is how we can use it for the end users. We will give two demos here. First demo is how we can use Spark Show to interact with HBase based on the SHCs. Secondly, we want how we can use Spark Submit Jobs by you can write your applications. So first, let's go to the Spark Show. Okay, this Spark Show already opened it. When you open this Spark Show, you need to register the SHC package here. Like you can set, okay, what's the package you should use and what's the mode you want to use, like a young cluster mode and young client mode, okay? After you open these shows, first we need to define the catalog. The catalog is the most important thing for the Spark HBase connectors. Because why? Because we need to define the mapping between the HBase and the Spark. Because, for example, in this catalog, you can see we have some table names, table coder method, and row keys, and column family and keys here. This way, you can represent the data in the Spark side. This part represents data in the HBase side. When you define this catalog, you can define the mapping between the HBase and the Spark. Okay, we copy here. Put into show. Okay, we define the mapping here. And then we can, first we did demo how you can write data into HBase. We can define some object here. Okay, don't have enough time, just go quickly. We define some object, and in this object, you have some keys, column 1, column 2, and column 3. And then we can use Spark to write data into HBase. Okay, save data into HBase. You can see we parallelize these data frames, and then we write the data into the HBase based on the mapping here that we defined before. First, we define the table catalog mapping, and second, we define how many region surveys should be used. For example, use 5 years. Next, after you write data into the HBase, you want to read data from HBase as well. Okay, we define some function here to read data from HBase. We use our predefined catalog before. Okay, almost done. Good here. We can read data from the HBase. Okay, this data frame is done. We can get show here. Okay, this is our data from HBase we write before. This is a very interactive, very basic interactive show to how you can use SQL to connect with HBase. We already provide some example in our GitHub repos. For example, how you can import the SQL based on the POM file here. For example, based on POM file here. Also, we can provide some very complex example in our example directory. Because the timeout, we just you can refer to the letters. Okay. Okay, we hand over back to the regions. Okay.
Okay. So here we just want to thank you, HBase community, to give us very good feedback and make this connector better. And we also want to thank you, Spark community, and all Spark HBase contributors, especially Zhang, to start this project. Really thank you. And there are some references. At last, if you have any question, you can email to us. Thank you. Any questions?
All right, thank you. Thank you very much. So we have time for a few questions. We have one microphone here, and if people want to come down this alley, I have this other microphone here. Do we have questions? We do.
Hi, you spoke about the fact that you guys cache the connection. So is the caching done per job or per partition?
Excuse me, you mentioned the cache.
Yeah, so in one of the slides you guys mentioned that you cache the connection.
Actually, we cache the connection object because when the S3C to visit HBase table, we need to call the create connection that function first to get the connection object. So because our customer have very long-living applications, they will visit tables and region servers again and again. That's why we need to catch the connection object.
Okay, so you cache it once and then reuse it throughout the job?
You mean?
So you cache the connection once and then reuse it throughout the job?
Yes, correct. If the object, has been there a long time and no one uses it, then there is some thread, clean thread to clean up it. Yes.
Okay, thank you.
Yeah.
Do we have some other questions? I saw a hand over there. Yes, please.
So just a follow-up question. So is that one connection per executor? Or I guess more general, is it just one connection or is it a connection pool that you cache?
You can say it's a connection pool.
Okay.
Yeah. Actually, this feature is supposed to handled in HBase side, but after discuss this issue with HBase community, they have some reason to remove that logic from current Apache HBase master code. Although it is be there in branch 1 releases, in HBase side. So that's why we need to handle that logic in SHBase, side. Yeah.
Yeah.
Okay.
Hi. You mentioned that the executor always runs on the region server. So in that case, how will you load balance? Say like I am running multiple jobs for this HBase, and there is no space to allocate any more executors on the region server. So will it block the job completely?
You mean, could you repeat your question? Sorry.
So in like slide 9, you mentioned that the executor always runs on the region server. Region server and the executor, they are on the same host.
Yes.
So in case like you are running multiple jobs and you need to create multiple executors for those regions, and there is no memory available, so will it completely block the job?
Oh, you mean, so let me repeat your question. So in our slides, we mentioned we deployed Spark and HBase in the same cluster. So the executor are co-located with the region server. So you mentioned if there are more executors available there, what will happen, you mean?
Yes.
Okay, so we will actually, Spark will choose the executor located with the region server first. If that executor are very busy, yes, they maybe choose the other available regions executor to do the task. But but the region server, if the region server not hold the required data, even there are more executor, it's not benefit to the application, right?
I mean, my question is like, executor cannot be spawned on the region server.
Oh, you mean the executor located with the region server cannot respond to the application, but there are more other available executor in other region server? Yeah, definitely we'll choose the available executor. So in that deployment, it means the executor will remotely fetch the result from the region servers.
Okay.
Yes.
Yeah, so for the interest of time, we need to stop the questions here, but I'm sure our speakers will be around still for taking a few more questions after that. Let's thank our speakers.
Okay, thank you.